In this course, we will build the foundation of a Minecraft-style game. In this first video, we will generate a world using a noise library to create a large terrain of blocks. We will also introduce a player that can fly or walk along the ground. This will require simple collision handling for the blocks. Finally, we will introduce a UI that allows us to display some debug information on the screen, like the player's position in the world. This build will make use of both blueprints and C++. To follow along, you will need an editor like Visual Studio or Rider set up to work with an Unreal project. In the next video, we will introduce the ability to change the world by picking up or placing blocks. To begin this project, we will clone the starter project that we have been using for many of the other courses. You can build this project for yourself by following the player controller video on this channel, or you can simply download the repo that is linked under this video. Now that we have the project open, begin by deleting the floor object. Let's also set the default open location to the main window, so all of our assets do not open in their own new window. Let's now create a new enumeration asset in the player folder. Call it eMovementKind. This will define the different ways in which the character can move. In this enumeration, create two variants, one called ground and another called air, then make sure you save this asset. Now, let's introduce an input action that will allow the player to switch between these two different kinds of movement. In the input folder, create a new input action called IA_switch movement. We do not need to change its type from the default Boolean. You can save the input action. Next, open up the input mapping context called IMCDefault. In here, we will introduce a new mapping for the switch movement action. We will bind this action to the Tab key. The next thing we want to do is extend the move action. This is because we want the player to also be able to move up and down when they are flying. Add two new bindings for the Q and E keys. We need to assign modifiers to these bindings so they are applied to the final action value correctly. These two keys will affect the Z component of the value. The Q key will move the player in the negative Z direction, and the E key will move them in the positive direction. So add a negate modifier to the Q binding, and then add a swizzle modifier as well. We need to change the order of the swizzle to ZYX. This will take the X value of the one-dimensional key input and move it over to the Z value where we actually want it by swapping the two components. Now, we just need the exact same swizzle modifier on the E key. The only difference is that it will not have the negate modifier, since we want its value to remain positive to move the player up along the Z direction. The input action itself will handle adding all of these inputs together before passing them along to the event handler. That completes our work on the input mapping context. Save and close this asset. Now open up the main character blueprint that already exists in the starter project. We will introduce a new variable called movement_kind with the type eMovementKind. We can set the default value to air so that it is easy to explore the world while testing by flying around. We can also turn on the option to automatically save the blueprint anytime we successfully compile. Now, let's update one of the settings on the character movement component. We are looking for the braking deceleration option under the flying section. Set this value to 2048. This will make it so the player will essentially stop right away when the player lets go of the input while flying around. This is mostly just to make the controls easy for testing. Let's now introduce a new function called setMovementKind. This function will change the current movement kind for the player. We will give it one input called inMovementKind, which will represent the new kind we are trying to set. To begin the body of the function, introduce a switch statement on the movement_kind variable we just defined. This will give us a code path to handle each type of movement. For the ground path, get a reference to the character movement component and then call setMovementMode on it. We want to select walking as the new movement mode. This is also why we couldn't name our enumeration movement mode. The character movement component already defines an enumeration called eMovementMode. Now let's copy these two nodes and then update the new movement mode to flying for the air path. Copy the character movement node again so that we can set the gravity scale for each path. For the ground path, set the gravity to 2, and for the air path, turn off the gravity by setting the scale to 0. That completes this function. Save everything and then close extra tabs to clear up the workspace. The next thing we're going to do is introduce the begin play event into the event graph. We will use the function we just defined in order to set up the player to begin the level flying. First, set the movement_kind variable to air, and then call setMovementKind and pass in the variable as the input. You can either pull over the wire directly from the setter or use a getter. I like to use a getter simply because it looks cleaner in the graph. Now, we want to introduce the switch movement event. We will begin handling this event by using a switch on the movement kind variable. Make sure you set the variable to the opposite of its current value in this case. If the player is in the ground state, we want them to now switch to the air state. After that, let's call the setMovementKind function on each path. You can once again either connect the wires directly, use a getter, or in this case I'll just manually set the input value for each path. That completes the response to the switch movement event. We now want to extend the move action so that it allows the player to fly when they have the air movement kind. Open up the move action function. To get started, we first have to update the type of the move input action, because it is currently a vector 2D. That is all we needed for the basic player controller, but now we want it to be a 3D vector. Open up the IA-move input action and change its type to axis 3D vector. In Unreal, a type that does not list its dimension is generally a 3D type because they are the most common. Make sure you save the input action before closing it. Now, we also need to update the input for the move action function because it has a vector 2D input to match the input action it is handling. Change the type to vector. If you try to compile now, you'll see that you get an error because the blueprint is still trying to call the break vector version for the 2D vector. First, return to the event graph and hook up the action value input. Now return to the move function and delete the break vector that is broken. If you just pull out a new wire from the updated input and search break, you'll now get the correct 3D version. Let's now move this entire response up above so that we have room for two different responses in this function. We'll start by using a switch on the movement kind variable again. We can connect the ground path directly to our old code, because that will remain exactly the same as before. To avoid pulling wires across the whole blueprint, we can also access function parameters directly by searching for them as a getter node. You can see they have a special icon and tooltip explaining that this value is the same as the one that was passed into the function as an input. Now, let's copy all of these nodes to help set up the air path, because this path will be very similar but with one added dimension. What we want to do is follow the exact same pattern. Take the new z value from the input and create a reroute node down below the other two. For this component, we want to get the actor's up vector. We can then multiply the input value by this vector to get the third contribution to the movement when in flying mode. All we need to do now is add a third pin to the addition node so that all three directions can affect the final movement when the player is flying. We should now be able to compile the blueprint without any errors. We can now begin working on the core of this build, which will be the generation of a voxel world. Create a new folder in the project called World. We will need the tile atlas image that is provided in the repo for this project. You can also use your own tile images. Just make sure it is also a 4x4 tile atlas with tiles that are 64 by 64 pixels. After we have this code up and running, you could also easily update a few constants to allow a tile atlas with more tiles or larger textures for each tile. To automatically create a texture asset, simply drag the tile atlas image into the world folder in the editor. You can now open the texture to take a look at it. Make sure you save the asset before moving on. The next thing we will do is create the material that will be applied to the blocks in the world. Create a new material in the world folder called m_block material and open it in the editor. We can now create a texture sample node from our texture asset by dragging it directly onto the material graph. Once we have this node, we can connect its RGB output to the base color for the material. We will also zero out the metallic, specular, and roughness values so the blocks simply display the texture without additional surface effects. You can also change the preview to a flat plane to get a better view of the material. Make sure you apply these changes before moving on. We will now introduce our first C++ class into the project. This class will represent the entire voxel world as a single actor. Under the Tools menu, choose the New C++ Class option. In this window that pops up, we can choose Actor as our parent class and then select Next. We can now set the name to be Voxel World and choose Private as the class type. We can then choose Create Class, and Unreal will begin setting up our project to use C++. This step could take some time to complete, especially the first time that you do this. Make sure you look out for any pop-ups because it might ask you for permission to open the project in your code editor. If everything is working correctly, your editor should probably open up on its own with the project loaded up. In Rider, you can view the active processes by clicking at the bottom of the editor. All of these loading processes will probably take some time the first time that we run this. This will go much faster in the future once everything is set up. In Rider, it will also likely prompt you to install the Unreal plugin. This is a very helpful tool. You will be given the option to install it into the current project or the engine itself. If you plan on building multiple C++ projects with Rider, then install it into the engine. On Windows, there might be some other pop-ups related to security permissions, so make sure your setup doesn't get stuck by a hidden window waiting for your input. Once everything is set up and the indexing has completely finished, it will likely jump back to the Unreal editor. We can now explore the project in the code editor. The source directory has the C++ files we have created for the project. This is where the majority of the work will be done. There is also one important C# file that starts with the project name and ends with build.cs. This file allows us to set some of the build settings for our entire project. For instance, it lets you define which engine modules you are using for this project. It also allows you to introduce new include directories that will be searched when you are trying to import files into your project. We will use all of these options shortly. The first thing we are going to do now that we have the project up and running is introduce a C++ library that will allow us to generate noise patterns. We will then use this noise to produce our terrain once we can place blocks in the world. Go to your browser and search for Fast Noise Light. You should be able to easily find the repo for this project on GitHub under an account called Auburn. Download the repo to your computer. We now want to open our File Explorer to view the files in our project. You can do this by going to the Open In menu option after right-clicking on your project in the code editor. We want to create a new folder called Third Party in our project folder. This should sit at the same level as the private folder that already exists. And then we can create a folder for this new library called Fast Noise Light. Finally, locate the C++ header that is included with the repo and copy it into the Fast Noise Light folder. If you return to the code editor, you should now see the new folders and the header. We will now update the build file for our project. Let's start by first organizing this list of modules a little more clearly by putting each one on its own line. After that, we can introduce two new modules that will help us create the geometry we need when generating our voxel world. We are not going to simply draw thousands of full boxes. Instead, we will look at only what is visible to the player, and then create a single mesh from just the visible faces. This will require us to create this geometry while the game is running. To do this, we will need a couple modules that are not included by default. Add Geometry Core and Geometry Framework to the list of public modules our project is using. If you simply save this file, you'll probably notice the code editor begins automatically resyncing your project. This is because changes to the build setup for the project require the project to be regenerated. After that is complete, we also want to add a new call into our build file. There is a built-in variable called private include paths. This will allow us to add new locations where our project will look for files when we try to include them in our code. We will use this to add a new entry for the third-party folder we just created. This will allow us to include the fast noise library in our code without any complaints from the editor. Let's now return to the Unreal editor, save everything, and then close it completely. We now want to make sure that we can actually rebuild the editor from our source project. Once Unreal is closed, press the Build button that looks like a hammer in Rider. You should see the Build window open near the bottom of the editor. it will generate some log information showing you the compilation and build process. At the end, you should get a message saying it was successful. Otherwise, if you mistyped something or have a flaw in your setup, you might see an error reported here. But if you do get a successful build, then you can attempt to run the project with the green play button. If everything is working correctly so far, you should eventually see the Unreal Engine splash screen appear, and then the Unreal Editor should load up just like it normally does when you open a project from the Epic launcher. Once it loads up successfully without any errors in the output log, you can close it again. We are now going to write a lot of the code before we run the game again, so we don't need to leave it running this entire time. We will now introduce a new C++ file from within the code editor directly, instead of creating the file from the Unreal editor like we did the first time. If you right-click on the private folder, you can find a menu item called Add. In the submenu, you can choose to add a new plain file. Call this file worlddata.h. In this file, we will define all of the core constants and data structures that we will use to build the voxel world. On my computer, the starter project already has a Git repo initialized within it, so that is why it will ask me if I want to add new files to the repo. Feel free to set up your own repo to help track the work you're doing on the project. Writer also has a nice version control interface that you can use to manage commits to your project repo. Now, open up the world data file in the editor. Begin by adding a pragma once include guard at the top because we start with absolutely nothing in this file. We will now define our first data structure for the voxel world. We are going to create an enum class that defines the different kinds of blocks that we will have in the world. Call this enum eBlockKind and use the uint8 type for the underlying value. But keep in mind, if you ever want to use more than 256 block kinds, then this will have to change to uint16. Let's begin by defining a none block type. This will represent a position in the world that has no block. Next, we'll introduce a name for each of the 4 block textures we currently have in our tile atlas. Call them green stone, blue stone, purple stone, and red stone. Finally, we also want to add one more variant called count. This is an old trick that will allow us to easily determine how many total variants are defined in this enum. It is not a real block kind, and will never reference it in that way. The next data structure we are going to define represents a single position in the voxel world. We will call each of these positions cells. A cell represents the empty space in the world where a block could be. And maybe in the future we will want a cell to have characteristics that are separate from blocks entirely, like temperature. This way, the idea of the position and the block itself are kept separate from each other. Introduce a new struct called fCell. F is the prefix Unreal has traditionally used to label pure data structures, just like E is the prefix they have used for enumerations. We will now define cell index, which uniquely identifies the global position of this cell in the whole world based on a single number. This is essentially like a unique ID for the cell, but it will also define its position in 3D space. We will go into details of this a bit later. Next, we will also give each cell a block kind field where we can set which type of block is present in the cell. Finally, we will introduce an 8-bit number called neighbor set. We will use this number to store which of the cell's faces are visible. We will do this using a technique called bit packing. This will be covered in more detail later in the video. That's all of the data setup we need to do for the moment. Let's go back to the Voxel World class and begin using some of these to set up the world. First, let's include the world data header in this file. This will give us access to the data structures we just set up. Let's also clean up this file a little bit. The Unreal template includes comments and formatting that I find a bit distracting. We can now add a new Unreal property that will hold a pointer to the player's pawn. We will use this later to display debug information about where the player is in the world. This uProperty line is an Unreal Engine reflection macro that is part of Unreal Engine. It labels the following variable as a property of this Unreal class. Properties carry some metadata and allow for additional features when they interact with the Unreal editor. For instance, a property can show up in the editor when we view an instance of this class in the game world. The macro can also take a series of input arguments that further define the capabilities of the property. Now, let's define another property called block material. This time we will pass in the argument edit anywhere to the macro. If you hover over the argument, you can see additional information about it. In this case, we want to be able to set the value of this field from inside the editor. That's why we have used the edit anywhere argument. We want this variable to have the type uMaterialInstancePointer. This type is essentially a copy of the material that allows us to make local changes for each object with the material without affecting the original material. Let's now introduce a private section of the header. Here, we will define an Unreal array to hold all of the cells for the world. Unreal's dedicated array class is called tArray, and we can provide the type of each element with a template parameter. We will call this cell array. Let's also introduce a new private function called generateWorld. It has no arguments. This will be the function we call at the beginning of play to build the shape of the voxel landscape. We can see that Rider is giving some warnings about two of the functions in the header. If we look at the warning for the tick function, it is simply saying that we have narrowed the scope of the function. It is defined as public in the parent class, and it is now protected in this class. I'm doing this simply for organization purposes. It looks cleaner to have the two built-in functions together. But the warning on generateWorld is different. It is warning us that we have not yet implemented this function in the source file. That is something we will fix shortly. Let's now move over to the source file, which was created for us automatically. It is called voxelworld.cpp. We will start by cleaning up some of the comments to help make the code clearer. Now, in the constructor, let's create a default root object for the actor. If we do not do this, then it will not have a transform component with a location in the world. Since this actor represents a physical presence in the world, we do want it to have a transform and location, so the root component is important. A reason you might not want a location for an actor is if it represents something more abstract, like a global timer for the world. In this case, it does exist in your world, and it does have actions, but it doesn't really have a position or a rotation. We can use the createDefaultSubObject function to create a new scene component to use as the root object. This is the simplest kind of object that has a transform. We then have to call setRootComponent to assign this new object as the root component for the entire actor. Now, let's go to the beginPlay function and make sure that the world actor is always at the origin. This way it doesn't add any additional position to our blocks when it generates them. We can do this by calling setActorLocation and passing it the 0 vector. After that, we will call the generateWorld function, which we still haven't implemented yet. We are now ready to begin building the foundation of the voxel world. In order to do this, we will define a series of constants that will determine the overall dimensions of the world we are building. We will define these constants in the world data header we created earlier. We will start by defining the size of each sector in cells. We will allow the sectors to have different size in all 3 dimensions. In Minecraft, the sectors are called chunks, and they are 32 blocks on the X and Y axis, but they are much larger on the Z axis. In the main world, the Z height is currently set to 384. For this build, we will also keep our X and Y sizes equal, but this is not necessary given how we're designing it. We will write all of the code so that the X and Y sizes could be different. We will first define the sizes as a power of 2. In other words, if the size we set is 3, then the actual number of cells is 2 raised to the 3rd power, which is 8. This will allow us to do some simple tricks when performing calculations on our world. So we will define 3 new constants, one for each dimension, and assign them default values. This means our test world will be 16 by 16 by 64. Next, for convenience, we will also define the actual number of cells for each dimension as a constant as well. We can get these values from the log base 2 values by simply shifting the number 1 to the left by the power of 2 we defined. For instance, we have 4 for the X size, so that means the total will be 1, 0, 0, 0 in base 2, which is equivalent to 16 in base 10. If you hover over the name of the constant, your code editor should also be able to show you what the final value will be. These are all const expressions, which means they will be evaluated at compile time before the program runs. Next, we will do the exact same thing for the size of the world in sectors. So each sector will be a large block of cells, and then the whole world will be a large block of sectors. Begin by defining the same log2 versions of these sizes, and then use the bit shift technique to get the final values. Also notice we do not need to define a z dimension for the world size, because there's only one sector for each XY position in the world. This is also how Minecraft is designed. Each chunk starts at the very bottom of the world and reaches up to the very top of the world. Now, let's use the world sizes to calculate the area of the world in sectors, because this will be useful in our code. We simply multiply the x and y sizes. Now we want to define constants that also give us the full size of the entire world in cells. Right now, we know how big a sector is in cells, and we know how big the world is in sectors. We can combine these two pieces of information to define a constant for how big the world is in cells. Notice that the z size technically would be multiplied by 1 because that is the size of the world in sectors for the z-axis, but we have chosen to leave that out for simplicity. Now we will create a constant that tells us what the full volume of the entire world is in cells. This is a count of how many total blocks could be placed into the entire world if it was completely filled. We will use this number as an easy way to iterate over the entire world when generating it. We will now define a series of variables we will call the stride of each dimension. We will go into more detail about this later, but it is related to the cell index we mentioned earlier. These values will help us convert from a cell index to the XYZ position of each cell. For right now, just define them in this way, and then we'll cover the details when we talk more about the indexing of each cell. Finally, we will define a few constants for the noise generation we will be using to create the terrain. We will define a float constant that determines the period of the noise output. This is essentially how fast the hills and valleys change in the terrain. A shorter period would mean sharper hills. Then we will define two more integers that determine the minimum and maximum height of the terrain that we are generating. That is actually most of the constants we will need for the entire build, so let's start using some of these to generate the world. We'll begin by returning to the Voxel world header. We are going to create a series of functions that will allow us to get information about the Voxel world. The first function we will define is called cellIndex2cellCoordinate. This function will take a cell index as input and return the XYZ position of that cell. We will use the term coordinate to refer to an integer grid position in the world, as opposed to a floating point decimal position. If we want to talk about a decimal position that can be anywhere in the world, then we will simply call those positions. A coordinate will always have integer components. This function will return a type called fIntVector. This is a built-in Unreal type that represents a three-dimensional vector with integer components. We will also make this function static because it will not modify the actor in any way. It will simply perform a calculation from its input and return the value. Let's now implement this function using the constants we just defined. Copy the function declaration and then go to the Voxel world source file. Paste the declaration into the file at the bottom, then delete the static keyword because it shouldn't be used in the source file. I also like to keep the return type on its own line to avoid really long function signatures. Let's now look at the idea behind converting a one-dimensional index into a coordinate position. We need to take a single number which uniquely labels each cell and convert it into three numbers that represent its x, y, and z positions in the voxel world. We will look at a simplified 2D example just to get the idea correct. This is where we will use the stride constants we defined earlier. The stride represents how much the index will change if we move along a particular direction. If we move along the x-axis, then the index will increase by 1 each step. Therefore, we will define the stride in the x direction as 1. This makes sense because if we were trying to map our index to a one-dimensional line, then the index would be identical to the coordinate. Every time our index increased by 1, our coordinate would also increase by 1, and they would always remain equivalent. But if we want to map to a 2D grid, then eventually the next cell index would wrap around to the next row. This would be represented as an increase by 1 in the y-axis. But that increase by 1 in the y direction represents a larger increase in the cell index. If we move from any cell up by a single position, then we have increased the index by 3 in this example. 3 is the width or size of the grid in the x direction. That's how we can see that the stride for the y direction is 3. Therefore, if we want to know what the index of the coordinate 1 above index 5 is, we can add 3 to that index. This gives us an answer of 8. We can use this information to figure out how far we must have moved in each dimension to reach any particular index. We do this by asking how many times does the index equally divide the stride in that direction. This tells us how many times we have increased by 1 in that direction. For this example, we can do an integer division of 8 by the stride of 3. This gives us 2, which we can see is the correct y value for the cell at index 8. We can then remove the contribution to the index that got us to the y coordinate and look at the remainder of the index to see how far we have moved along the x direction. We can figure out how much of the index was used up getting to the y coordinate by multiplying the coordinate by the stride. This gives us 6. Then we can subtract that from the index to get the remainder. Now we can apply the same process to this remainder to figure out how many times we have moved along the x-axis to get to this particular position. So we take the remainder, which is 2, and we divide it by the stride in the x direction. This gives us 2 divided by 1, which is 2, and that is the correct x component for the cell with index 8. This same process can be extended to any number of dimensions as long as we always start with the direction that has the largest stride and work our way downwards, always using the remainder from the previous step until we reach the first coordinate with a stride of 1. All we need for this algorithm is to calculate the stride for each dimension one time at the start before we need to calculate any particular coordinate. Remember, the stride is simply the number of indices that you have to travel through to get one position higher in that dimension. In the case of the x-axis, this is always 1. In the case of the y-axis, the cell index needs to increase by the size of one full row of the x-axis before y will increase by 1. And finally, when we add a third dimension, to increase by 1 in the z direction, we need to go through one entire slice of the xy plane before the z component will increase by 1. That is equivalent to the area of the slice. So the stride in the z direction will be the area of one of the xy slices. If you think about starting at index 0 and increasing the cell index until the z component increases by 1, then you'll see that you need to increase by exactly this area. Let's now apply this algorithm to create our first mapping function. When implementing this function, we will start with the z-axis because it has the largest stride. We can calculate the z component by dividing the cell index by the stride in the z-axis. We can then calculate how much that component contributed to the final index by multiplying it by the stride. All we are doing here is manually calculating the remainder of the division we just did in the first line, because we basically want to see what is left in the cell index after we have accounted for the component with the largest contribution. Keep in mind that we are doing integer division, so cell z is a whole number, it is not a decimal. Now, we can take the remaining cell index and apply the same process to figure out the y component. We divide by the stride in the y-axis and then remove the contribution from the cell index. Finally, this last step is included in the code just to make the intent easier to understand. If you look at the last two operations, you'll see they essentially accomplish nothing. We are first dividing by the stride in the x direction, just as we did in the other directions, but that stride is 1. So this does not change the value. We could just set cell x equal to the remaining cell index, and this would work exactly the same. And then we subtract the remaining contribution. But if everything about our math is correct up to this point, there shouldn't be any more remainder, so this last step will always produce 0. If you wanted to, you could actually assert that cell index equals 0 at this point as a way of making sure the math remains consistent. Now, we can return our final vector by packing all three components together. This will take a one-dimensional cell index and translate it into a coordinate in three-dimensional space. This function will be useful because we are storing our cells in a one-dimensional array, but we will often want to think about each cell based on its coordinate in 3D space. We now have enough in place to begin writing the generateWorld function. The first thing we will do is include the fast noise light header we set up earlier. Let's now implement the generateWorld function at the bottom of the file. We will start this function by allocating memory for all of the cells we need in our cell array. We can use the function setNumUninitialized to allocate the memory without constructing all of the cells with default values right away. We will use the worldVolumeInCells constant to determine how many total cells to allocate memory for. The next thing that we need to do is set up a fast noise light object. There are a series of functions we can call to define the basic characteristics of how it will produce noise values. We will first set a seed value so that we always get the same output for testing purposes. Next, we will choose the type of noise to generate. Simplex is an algorithm that was created by the same man who created Perlin noise, but was intended to be an improvement on the process. In general, it will be better for generating noise in higher dimensions. We will then set the frequency of the noise, which is how fast the noise goes between peaks and valleys. I find it much more intuitive to think about the period of noise when working with terrain. The period is the distance between peaks and valleys. For this purpose, we defined a constant called noise period. And to convert from period to frequency, we can simply take the inverse. This is 1 divided by the period. We will then set 4 values that determine how the overall shape of the noise changes. They are each referred to as fractal properties. You can dramatically change the overall look of the terrain by changing these 4 values. So after we finish this build, you might want to come back and test out changing them. Before we begin generating each block, we want to store the total number of block kinds into a variable. We can get the value by casting the count variant to an integer. We can now set up a loop that will visit every cell in the world. To do this, we will iterate over every cell index. We can get the total number of cells using the size of the cell array. We could also use the world volume in cells constant, but this way we can also make sure that the cell array has the correct number of items by relying on it. The first thing we will do each iteration is calculate the coordinate for the cell at that index. This is where we will use the function we just defined. We can then use the x and y components of this coordinate to generate a noise value. The generator will produce relatively smooth noise values. This means that if 2 points are close to each other, they will also have noise values that are relatively close to each other. This will ensure that we get rolling hills and not a terrain of sharp spikes. We have to cast each component to a float because the getNoise function expects float inputs. The next thing that we want to do is normalize the noise output. This is because the library produces values between -1 and 1, but we want our noise values to sit in the range between 0 and 1. To do this, we can simply add 1 to the final value and then divide it by 2. In this case, we will multiply by 0.5 instead of dividing by 2. This will first shift the noise value up into the range between 0 and 2, then it will scale that value down so that it is between 0 and 1. To get the final terrain height, we need to convert this normalized value to a size that matches our world's proportions. We can do this using a linear interpolation. We have already defined two constants for this purpose. We have a minimum and a maximum terrain height. We will use the noise value as the alpha in the interpolation, and then use our constants as the 2 points to interpolate between. In the end, this will produce a number between a and b according to how far alpha is between 0 and 1. Finally, we need to round this value to an integer because our terrain blocks only exist at integer coordinates. This gives us exactly what we need to know how to generate each block. First, we'll get access to the cell at this coordinate. We can do this directly by using the cell index. We know all of these indices are valid because we are only iterating through the cells we just allocated at the beginning of this function. We will also cache the cell's index for easy future reference. And then we will check to see if this cell is above or below the terrain height we just calculated. If it is below the terrain, then we will pick a random block kind and place it at this coordinate. We can choose a random block by picking a number between 1 and the total number of blocks. We are starting at 1 because 0 is block kind none. If the cell is above the terrain height we just calculated, we will set it to have no block at all. That is all we need to do to generate blocks for the terrain. We will now move on to creating the meshes that we will use to actually display this terrain in the world. Right now, we have all of the data we need to describe the world, but we need a way to actually display that data as geometry in the world. To do that, we need to generate meshes for each sector of cells. To create the meshes, we will first need to calculate a bit more data about the world we just generated. We only want to create geometry for block faces that are potentially visible to the player. So we need to calculate which faces are exposed for each block. We will start this process by introducing a couple more mapping functions. Create a new function called cellCoordinateIsValid. This will check to see if a cell coordinate represents a position inside of the voxel world. For instance, any coordinate with negative values would be outside our world. There would be no block data for it, so we don't want to accidentally try and draw it. We will also introduce a function that will get a reference to a cell when given a coordinate. This way we don't need to run the conversion from cell index to cell coordinate every time ourselves. Finally, we will introduce a function that will actually calculate the exposed faces for a particular cell. Let's now go back to the world data header for a moment to define another data structure. We will create a new enum class called e-axis direction. This will represent the 6 directions of the voxel world. These are equivalent to east, west, north, south, up, and down. We will also make use of a macro that is defined by Unreal that allows us to iterate over the values in an enum if we provide it the total count. We can do this using the count variant we always define for the enum. Notice, it says it will only iterate over a number of variants equal to the count. The count variant itself is actually the count plus 1 value in the enum, so it will not be included in this range. This is exactly what we want. We will also define an array that holds a vector offset for each of these directions. This is the unit vector that will move us along the respective direction. These will be useful for finding the neighbors of a cell. If we want to find the positive x neighbor of a cell, we will simply take the cell's coordinate and add the positive x offset to find the neighbor's coordinate. To make this work, these two data structures must have the exact same order, so be careful when defining these. Let's implement the mapping functions we just declared so that they are available for calculating the neighbors of each cell. To keep things ordered correctly, I usually like to go back to the header and then jump to a function that is right above or below the new function I'm going to implement. This way I know exactly where to put the function to keep the same order that exists in the header. This first one will be a very simple function. We simply want to test to see if the cell coordinates components are in the valid ranges for each dimension. This means they are greater than or equal to 0 and less than the size of the world in cells for that dimension. We can then combine all of these conditions together into a single Boolean with AND to get our final result. I also like to wrap it in an unnecessary parenthesis just to make it look cleaner. Now, let's go back to the header because there is one more mapping function we want to declare. This function will be the inverse of the first function we wrote. It will take a cell coordinate and convert it back to the matching cell index. In this case, we can use the same stride values to undo the process we did with the first function. In order to build up the index, we will multiply each coordinate by the stride for its dimension and then add them all together. This is exactly the inverse of what we did before when we divided by each stride, then subtracted from the index until we unwrapped each coordinate out of the index. Now we are multiplying by the stride and then wrapping them all together into a single index that has contributions for each dimension. If we jump back to the header, we can see that Rider is warning that we haven't implemented these functions, even though we just wrote code in the source file for them. If we go back to the source file, we can see the problem is that we did not designate these functions as members of the Voxel World class. This means Rider is assuming they are free functions that are not methods of the class. That's why it thinks there are no implementations yet. We can fix this by adding the class to the name of the functions. When we return to the header, we can see the warnings have disappeared. Let's now implement the getCell function. Copy the signature from the header. This function is just a simple helper so that we don't need to call cell coordinate to cell index every time we want to access a cell based on its coordinate. But notice, we are not checking to see if the coordinate is valid, so this could cause memory access violations if we passed it an invalid coordinate. This means we will need to check to make sure the coordinate is valid before calling this function. Now we have everything we need to implement the function that calculates the neighbor set. Again, copy the signature from the header and paste it into the source file. This function will calculate the faces that are exposed for each cell, and then it will store them in an 8-bit number using a technique called bit packing. We will interpret the patterns of zeros and ones in a binary number as separate pieces of data with their own types. Often, the simplest way this technique is used is to interpret each 0 or 1 as a true or false value. That is exactly what we will do here, but that is not the only way data can be packed into a binary number. In this example, since most systems will implement a Boolean value as a 32-bit number, we can already see how much more efficient it could be to store these 8 Boolean values in a single 8-bit number. If we stored these all in a Boolean type, it would take up 256 bits. We will use this technique to store the visibility of the 6 neighbors for each cell. Given that we need to store this information for each cell in the entire world, you can see why using 32 times the amount of space could lead to serious performance issues for large worlds. We only have 6 directions we need to store, so 2 of the bits will be unused. But that is a very small waste compared to the number of bits we would use to store these all as individual booleans. If we had 6 booleans for each cell, it would still take 192 bits. Let's now go back to the code and actually calculate the neighbor set for each cell. We will start by defining a uint8 with a default value of 0. This is equivalent to setting all of the booleans to false. We can now make use of the macro that gave us the ability to iterate over the axis direction enum. To do this, we need to use a for loop that iterates over the tenum range class with a template parameter for the axis direction enum. We can now cast the direction to an integer to get its index in the enum. And then we can use that to look up the matching direction offset. We can get the cell coordinate for the cell we want to test by first converting the cell index to its cell coordinate. Then we will make sure this is a valid coordinate, because we might be at the edge of the map where there are no valid neighbors. To do this, we just need to add the direction offset that we looked up to the cell coordinate to find the neighbor coordinate we are trying to test. If this is a valid neighbor cell, then we can get the cell object using our new getCell function. And if this cell is any solid block, then we will set the bit associated with this direction to be true, because we have found a neighbor in this direction that will block the face. To set a bit, we can use an operator called a bitwise OR. It will create a new binary number that will have a 1 in a position if either of the two inputs had a 1 in that position. This is exactly what we want to keep the original mask values and only update the 1 bit we are trying to set. Notice we can create the correct binary number for the operation by using the left bit shift operator. This takes the number 1 and shifts it to the left by the value of direction index. We then OR this with the existing neighbor set to update the targeted bit. Finally, after checking all 6 directions, we return the neighbor set that we've calculated. It will now encode a true or false value associated with each of the 6 faces for a cell. Later, we will test these masks to see which bits are set when we build the mesh for each sector. We are now in a position to finalize the generateWorld function. At the bottom of the function, after we've placed all of the blocks to create the terrain, we can iterate over each cell one more time and calculate its neighbor set. Notice that we can't do this in the original loop because we are still setting up most of the neighbors when we first visit a cell. In the next video, when we allow the player to update the world by changing blocks, we will need to think about how to carefully update its neighbors and then rebuild the mesh for that sector, or possibly sectors right next to it. We can now get into building the sector meshes that we will use to render the blocks in the world. Return to the world data header so we can introduce some new data structures. First, add a new struct called fSectorFace. This struct will have a block kind and a direction, and we will also store the cell coordinate where it is located. This struct will represent one block face. We need to restrict blocks down to individual faces because when building the mesh, we might only have a few faces showing for a block. We can then introduce another struct called fSectorMesh. This will represent all of the sector faces that make up the rendered version of the blocks in a single sector. We will store the sector index and then an array of sector faces for each sector mesh. Let's now return to the Voxel world header so that we can add a new private variable that will hold all of the sector meshes we build. We will add an array of sector meshes. Each sector will have an index just like the cells do, and we can use this index in the same way to organize the 2D space of sectors. Now we can also introduce 2 new functions that will manage the building of the sector meshes. The second function will build an individual mesh and then return it. The first function will call that function for each sector in the world. Let's now implement these 2 functions. Copy the function signatures from the header and then jump to the right place in the source file by navigating to the Generate World function. Now paste them into the file and format them correctly. Make sure you remember to include the class name to designate them as methods, not free functions. We also need to write a series of mapping functions for the sectors in order to build the meshes. So let's go back to the header one more time and declare the 4 functions we'll need. These functions will be very similar to the cell functions. We will define a function to check if a sector coordinate is valid, and then we will define 2 functions we need to convert from index to coordinate and from coordinate to index. Finally, we will define one more function that translates across sectors and cells. We will sometimes want to know what the cell coordinate is for a particular sector. This will be the cell that has the lowest coordinate in the sector. This function will be called sector coordinate to cell coordinate. Now copy all 4 of these signatures and paste them into the source file in the correct place. Make sure you remove the static keyword because it should only exist in the declaration. We will now go through them one by one. They are all very similar to the logic we used for the cell functions. To check if a sector coordinate is valid, we just need to make the same kind of range check, but we want to make sure we use the correct world size constants this time instead of the sector size constants. In order to get the sector coordinate, we will essentially do the same thing we did with the cell coordinate, but we will use a bit of a shortcut since we only have 2 dimensions. In this case, there are 2 operators that will give us exactly the values we need for each component. The modulo operator will return the remainder of a division, and the integer division operator will return the quotient. These are the exact same values we calculated using the division and subtraction for the cell index, but since 2D is simpler, we can use this shortcut. This is actually how you'd normally see this algorithm done, because it's so common to go between 1D and 2D. But we looked at a much more generalized version of the algorithm which can be extended to any number of dimensions when we did the cell index. We actually don't need these casts because the operators both return integers. We will build the sector index from the coordinate in exactly the same way, just making sure to always use the world size constants for these functions. Also, notice we could have multiplied the x component by 1 to represent the stride in this case, but we are leaving it off for simplicity. The 2-dimensional case is fairly straightforward to read either way. And finally, we will calculate the cell coordinate of a sector by just multiplying the sector coordinate by the size of a sector in cells. This will give us the cell coordinate for the lower corner of that sector. Since sectors always start at the bottom of the world, we don't need to calculate anything for the z component. It will always be 0. That gives us all of the mapping functions we need to write our sector mesh function. We will start this function by creating a new sector mesh that we can fill with the faces. We can construct the sector mesh with the provided sector index and an empty array of faces. After that, we will set ourselves up to iterate over all of the cells in the sector. To do this, we will first get the sector coordinate from the index, and then use this to get the cell coordinate of the lowest cell in the sector. This cell will be our starting point for iterating over the whole sector. The first iteration will be over the z dimension, which is the simplest because this will always go from 0 up to the full size of the sector in the z direction. Then we want to iterate only over the x and y coordinates that are contained within this sector. To do that, we will start each iteration at the sector cell coordinate that we just calculated, and then iterate until we hit the end of the sector. This will be after we have traveled sector size in cells. To start the body of the loop, gather the 3 components into a single vector for the cell coordinate. We will then test to see if this is a valid cell coordinate. This check should not be necessary, but we'll do it just in case. If we find an invalid cell, we can just skip the iteration. Next, we will get the cell at this coordinate and then check to see if it is empty, or if its block kind is none. If it is, then we'll also skip it because there will never be any sector faces emitted for a cell with no block in it. Finally, we want to iterate over the 6 axis directions again and check to see if any of them have their neighbor bit mask set to true. We can perform this check in a very similar way to how we set the bit in the first place. First, we get the index of the direction, then we create a mask from it. And finally, we use the bitwise AND operator to test whether the bit is set. If the bit is not present, then there is no neighbor in this direction. which means that we should create a face for this direction because it is exposed. This is because there is no block that is hiding the face from the player. The bitwise AND operator can be used to test if a bit is set, because it will only return a 1 in a position if it is set in both inputs. We can create a bit mask that represents the bit we want to test, and then apply the AND with the neighbor set. Since our bit mask has zeros in every position except the one we are testing, it will always return a 0 for those positions. The only place it will ever return a 1 is if there is also a 1 in the matching position in the neighbor set. This is exactly the result we want. In order to check the result, we simply have to ask if the final result equals 0. If it does, then the bit was not set, because we got back a number with zeros in all positions. This means our test bit mask did not have a matching bit in the neighbor set. So we can use this operator to test each direction. If we find a direction that is visible, then we can create a new sector face, passing in the values from the cell along with the direction we are testing. And finally, we can add this face to the sector face array in the sector mesh. The last thing we need to do is return the sector mesh that we've just built. Now we can write the build sector meshes function using this new function. All we have to do for this function is empty the sector mesh array in case we are trying to rebuild the sectors, and then iterate over each sector index, calling build sector mesh for each one. We can then add those sector meshes into the sector mesh array we defined earlier. We can now call this function in begin play so that it builds all of the sector meshes right after we generate the new world. To make sure there are no errors so far, let's now build the project again. We still won't see anything yet because we have only generated world data at this point. We have not created the final piece, which will be the components that will render the geometry. But we just want to make sure all of our functions run without any problems so far. After the project builds successfully, run it. We can now add our Voxel World actor into the level. Let's reset it to the origin, although this will also be done by our code whenever we press play. Then run the level and make sure you see no errors. You can also take a look at the components for the Voxel world and make sure the root component was created successfully. If it wasn't, then you will not have a transform component where you can set the location. Alright, everything looks good so far, so let's close the editor and move on to the last part of this build where we'll actually see these meshes rendered into the level. We will now create a component that will render each sector mesh in the world. It will also handle the collision with the player. We are now going to create a new Unreal class by right-clicking on the private folder and selecting the Unreal class option. We will call this new class Sector Component. We need to select the All Classes tab so that we can find the UDynamic Mesh Component parent class. Also make sure the private class type is selected before pressing OK. This will automatically generate a header and source file for our new class with some boilerplate content. Let's clean up the header in the same way we've done before, then include the world data header. We also need to include the header for the Dynamic Mesh 3. This will give us the functions and types we need to create a new dynamic mesh for the sector. We can also remove the arguments to the uClass macro. We do not need them for this component. And we can completely remove the begin, play, and tick function. For this class, we only need to define two functions. We will define a public function that will be called to create a new dynamic mesh from a sector mesh. Make this function static because it will not directly modify the class instance. Then define one private function that we will use to convert a block kind into the relevant UV coordinates for its texture in the tile atlas. We will use this function to essentially look up what texture matches each block kind. We now need to introduce one final set of constants. These will define the dimensions of the tile atlas. First, define two constants that represent the size of a single texture in pixels. Then, define two constants that will represent the dimensions of the tile atlas. This is going to be the total number of tiles it has in each direction. In our case, both of these values are 4, because our tile atlas is a grid of 4 textures. Now we want to calculate the size of each tile in coordinates relative to the texture itself. Since UV coordinates go from 0 to 1, we can find this value by dividing 1 by the number of tiles in each dimension. This is equivalent to the total size of the texture divided by the number of textures. This is essentially the normalized size of each tile, where we assume the total size of the texture is 1. We will also define one last constant that is unrelated to the tiles, but it's the last constant we will need for the entire build. Call it sector view range. This represents the total number of sectors that the player will be able to see in each direction. The next thing we are going to do is define the vertices for each voxel. We only have to do this once, and then we will translate these vertices to any position in the world where we want to place a voxel block. Define a multidimensional array of floats called voxel vertex array. The dimensions represent the number of faces for a voxel. the number of vertices per face, and the number of coordinates per vertex. Now we need to define the vertices for each face. We want to make sure we keep the exact same order we defined for the direction enum. The vertices will be defined with one corner of the voxel at 0, 0, 0 and the other corner at 1, 1, 1. And they will be defined in counterclockwise order for each face. Let's now implement the functions we declared for the sector component. Begin by deleting all of the boilerplate for the functions we no longer need. We'll start with the private helper function for calculating the UV coordinates for a block kind. The first thing we will do is use a built-in Unreal function to assert that the block kind is not none. This is because there is no texture for the none block, so we want to catch ourselves if we ever accidentally ask for its UV coordinates. The math here will be very similar to the calculations we did to convert an index into a coordinate. This is because the block kinds are organized in the tile atlas in the order of their index in the enum. This means we can do the same trick to find their coordinates in the 2D grid. We will first calculate the index for the block, and then we will use the modulo and division operators to find the correct coordinate. The only difference is that we then have to divide by the number of tiles so that the coordinates are valid UV coordinates between 0 and 1. We do not want coordinates like 3, 0 because that will not be correct for a texture UV. It would be the correct grid location on the tile atlas. Be very careful with the names here because the first two should be tile atlas size U, but the second two should be U and V. This is simply due to the algorithm we are using for converting indices to coordinates. With the index, we want the remainder and the quotient of the same division to find that coordinate. But when we are normalizing these coordinates, we want to normalize each according to the correct size for its dimension. Because our tile atlas has the same size in both directions, we wouldn't have noticed this error right away. But if you later want to use a tile atlas with a different width and height, you might have ended up with a very difficult bug to locate. Now we can write the build dynamic mesh function. Begin by defining a new dynamic mesh object. We will also need to call enable attributes on this object so that it is ready to have UV coordinates assigned to it. We will now iterate over all of the sector faces in this sector mesh. The first thing we want to check is whether the block kind for this face is none. This should never be true, so we might want to change this to an assertion later on, but for now, we'll just skip any face that has no visible block. The next thing we're going to do is get the direction index for this face. This will be necessary for looking up the vertices in our voxel vertex array. We also need to calculate the position of the cell. We can simply convert the integer coordinate directly into a float vector using a constructor. After that, we are going to do something simple that looks confusing because of the old C-style syntax. We want to get a reference to the part of the voxel vertex array that defines the one block face we're dealing with. To do this, we have to use a strange syntax, but we are just defining a variable called vertex array that is a reference to the array of 4 vertices for this face. We can then use this reference to define all 4 vertices for this face. Once we have these vertices defined, we can append them to the dynamic mesh. We will also need to go back and define one more constant that we are missing in the world data header. Call this constant cell size in centimeters and set its value to 100. This will give us voxels that are exactly 1 meter. This is the same size used in Minecraft. Now we can return to the sector component source file and append the 4 vertices. We need to make sure that for each vertex we add the cell's position to the vertex position and then multiply the whole thing by cell size in centimeters. This will ensure that the base vertices are translated and scaled to the correct position in the world for this particular face. Notice that we need to store the return value of these operations because these indices will allow us to reference the vertices when we create the 2 triangles that will make up each face. We can now call append triangle to create the 2 triangles. Make sure you pay close attention to the order here, because it defines the winding of each triangle, and that determines which side of the triangle that is visible to the player. Also, notice that we are referencing the vertices using the index that was returned, not by using the vector itself. Now we can get a reference to the UV overlay for this new mesh. We will be able to use this to apply the UV coordinates to map the texture to the mesh. To do this, we need to use the helper function we defined earlier in order to calculate the location of the block's texture in UV space. We can then calculate the UV position for all four corners of the block face by adding the correct tile size variable combination for each vertex. Notice that I'm adding an unnecessary +0 just to make the code clearer. It doesn't actually accomplish anything and will probably also be optimized out by the compiler. Finally, we can add these coordinates to the UV overlay using the append element function. We again need to store the indices that are returned so that we can define the same triangles for the UVs that we defined for the vertices. We can then call setTriangle on the UV overlay and use the UV indices to reference each coordinate. Make sure that you keep the exact same pattern that we used for the vertex positions. Now we need to return the dynamic mesh we've just built. That is all of the work we need to do on the sector components. Let's now return to the Voxel world and make use of these components to render the world we've generated. Begin by including the header for the new sector component class. We want to define a data structure to hold the sector components, but this is a bit more complicated than the sector meshes. In the case of the sector meshes, we create all of the meshes and reference them whenever we need them. But when it comes to the sector components, we only want them to be active when the player is near them and can actually see them. So the first difference is we do not need to create an entire world of sector components. We only need to create enough to cover the view distance around the player. So we will create a pool of sector components, and then whenever the player moves into a new sector, we will regenerate the dynamic mesh for the sectors in this pool. That way, we don't need to continually create and destroy sector components as the player moves around the world, and we can dramatically decrease the total number of sector components we need to create. To keep track of the pool, we will actually declare two data structures. One will be a map from a sector coordinate to a sector component pointer. This will allow us to easily look up which sector component exists at a certain sector coordinate. The other data structure will keep track of which sector components are free to be used from the pool. Both of these data structures will have pointers to the same set of sector components, but we will constantly update which components are referenced in each structure. We will also introduce 4 functions that will be used to manage the sector components. The first function will be called init sector cache, and it will be run on begin play to create the initial pool of sector components. After they are first created, they will then all get placed into the free sector component array. Then we will declare a function called update sector components that will be run every time the player moves into a new sector. This will determine which sectors need to be drawn and then update the dynamic meshes to match them. Finally, we will introduce 2 functions to add and remove sector components from the active sector component map. These will handle the management of the 2 data structures while the player is moving around the world. Let's now copy these function signatures and jump to the correct place in the source file to begin working on them. We will start with init sector cache. We first need to calculate how many total sectors can be seen at any one time. To do this, we will take the sector view range and then multiply that by 2 and add 1. That gives us the total number of sectors that will be drawn in one dimension around the player. Then we just have to square this number to get the total number of sectors that will be visible around the player. Once we have that number, we can use it to create a loop. For each iteration of this loop, we will first generate a unique name for the component by using the current size of the free sector component array. This will start out at 0 and then go up by 1 every time we create a new sector component, so it will always be unique. Next, we will call newObject to create a new sector component using this name and the voxel world as its outer parent actor. We will then attach the component to the root component we created for the voxel world. We also want to set the block material so it will know how to draw its block textures. And then finally, we will add this new component to the free array. That's all we need to do for this function. But let's also go to the begin play function and make sure we call this new function. Let's now write the add and remove functions so that we can use them to write the last function where we update all of the sectors the player can see. To begin the add function, we first need to get the sector index from the coordinate. We can then use that index to look up the sector mesh itself. We will then simply assume that there is always a free sector component we can remove from the free array. We can now call the sector component function we defined to build the dynamic mesh. This is a static function, so we do not need an instance to call it. Instead, we use the class name to reference the function. This will generate a new dynamic mesh for this sector. We can now set up the component using a series of function calls. We will register the component with the game system and ensure it is visible. We will also turn on collision and set it to immediately generate collision for the mesh. Finally, we can get the dynamic mesh and set it to the new mesh we just built. We also want to notify the system that the mesh has been changed. We will then add this sector component to the active sector component map. So this sector component was removed from the free array at the beginning of this function and then added to the active map at the end. We always want to make sure we maintain this accounting. Now we'll write the remove function. In this function, we first want to see if we can find this sector component in the active map. If this returns a valid pointer to the item, then we know it's safe to remove it. We can then dereference the return value because find actually returns a pointer to the item it was looking for. But the item we are looking for is itself a pointer. This means we need to dereference the return value one time before we get down to the sector component pointer we are actually looking for. What was technically returned by the find function in our case is a pointer to a pointer. We can now undo many of the things we did to the component when it was added. We can set its visibility to false, we can turn off its collision, and we can unregister the component. We can then add the component back into the free array and then remove it from the active map. That's all we need to do for the remove function. We can now write the update sector components function using the add and remove functions that we've just completed. To begin this function, we'll first check to make sure the block material has been assigned. We have exposed this property in the Unreal Editor, so it needs to be selected by the user from the editor. If this has not been done, then none of these components can be rendered, so all of these updates would be useless. We will now define a series of data structures called sets to track what sectors need to be added and removed. A set is a collection of unique items, which means that if you add the same item to a set twice, it will only retain a single copy. That's what makes it different than just an array. We can also take the difference of two sets. We then get another set that has all of the items that are in the first set, but not in the second set. We will use this difference operation to figure out what sectors need to be added and removed. We will first define a set that stores all of the sector coordinates that are currently being rendered. We will then define a second set that stores all of the coordinates we want to render in the next update. We can get the current sector coordinates by just copying the keys of the active sector map. To figure out what sectors need to be rendered next, we will iterate over the sector view range in all directions around the player. We can then check each coordinate to see if it is a valid sector and then include it in the next set if it is. We are missing one important piece of information though. We need to be able to figure out what the player's current sector coordinate is. Let's return to the header and define three new variables related to the player. The first one is unrelated to our current problem, but we'll need it soon. Create a float called player location offset. Next, define a variable for the player's cell coordinate and then another one for the player's sector coordinate. Remember that the cell coordinate is a 3D integer vector and the sector coordinate is 2D. We will make sure to update these variables in a moment, but let's go back to the function we were working on and use them to finish it up. After calculating the sector coordinate, we check to make sure it is a valid sector. If it is, then we can add it to the next set. Now we want to create two new sets that will represent the sectors that need to be removed and those that need to be added. We can get exactly those two sets by first taking the difference between the current and next set, and then taking the difference between the next and current set. If we ask what coordinates are in the current set, but not in the next set, then these are exactly the coordinates that need to be removed. And likewise, if we ask what coordinates are in the next set, but not in the current set, then these are exactly the coordinates that need to be added. This also means that if a coordinate was in both the current and next sets, it will be left alone. This is exactly what we want, because it is a sector that is still visible, so it doesn't need to be removed, and it was already rendered in the current set, so it doesn't need to be added either. To complete the function, we just need to iterate through both sets and call the matching function. We now want to call this function once at the end of begin play, so that the player has sectors rendered around them at startup before they have moved to a new sector. Now let's handle the tracking of the player's location. Return to the Voxel world header and declare a new function called initPlayer. Then implement this function in the source file. To get information from the player, we'll need to include a few more headers. Include the character class, the capsule component, and the gameplay statics header from Kismet. Now return to the initPlayer function. We will first calculate a position to start our player. We will place them at the very center of our voxel world. To do this, we will divide the size by half in every dimension and then multiply by cell size in centimeters. We have to do the multiplication by cell size in centimeters because our coordinates are in meters, but Unreal's basic unit is the centimeter. So anytime we actually want to render something, we need to have it converted into Unreal's units. After that, we'll initialize the player sector coordinate to an invalid value of -1, -1. This will trigger an immediate update of the sector components, because the player's new sector coordinate right away will be at the starting position, which will be different from -1, -1. We can now use the gameplay statics function to get a pointer to the player pawn. We will check to make sure we have a valid pointer and then set the player's location to the center of the world. We will then cast the pawn to the character class so that we can access its capsule component. What we want to do now is calculate the offset we need to use to locate the center of the cell the player is standing in, because that is the actual position we want to use when calculating where the player is located in the world. If we can't get a valid character from the cast, then we will just revert to using 0 for the offset. It will just report a slightly incorrect cell coordinate for the player. Now we can call the initPlayer function in begin play right before we initialize the sector cache. We are now going to introduce two new functions that will help us figure out where the player is in the world. These two functions will take a location in the world and convert it into a cell coordinate or a sector coordinate. Let's implement these two functions in the source file. For the world location to cell coordinate function, we can simply divide the cell coordinate by cell size in centimeters. This will give us the world location in meters, and then we can use floor to integer to drop the location down to the nearest integer. Due to the way we defined our cell coordinates, this will give us exactly what we want. Of course, it will also work for technically invalid cell coordinates, but we also want that as well. Because even though there are no voxels to render in those positions, it might still be useful to report for debugging purposes if the player is in one of those invalid cells. We can also do something similar for world location to sector coordinate. First, we'll get the cell coordinate using the function we just defined. This will handle much of the conversion already. We can then bit shift the cell coordinate to the right by the log2 sector size we defined earlier. This is equivalent to doing integer division by the sector size. It will divide by the sector size without producing any remainder. This is exactly the sector coordinate calculation we want. But this only works because we've defined our sizes as powers of 2 and then defined these separate log2 versions of the sizes. Let's now go back to the tick function to update the player's location. We will first check to make sure we have a valid reference to the player pawn. Then we can get the pawn's location and subtract the offset we defined earlier. This will ensure it points to the correct cell that contains the player's feet. We first want to call world location toCell coordinate and store it directly in the variable we defined for this purpose. But then we want to check to make sure we need to update the player's sector coordinate. We don't want to run the update if the player is still in the sector they were in last frame, because the sectors they can see will not have changed. So we check to see if the sector coordinate is different from the one we stored in our variable. For the first frame, this will be true because we set player sector coordinate to an invalid value of -1, -1. If the coordinates are different, we will update the variable, but then we will also call our update sector components function to ensure the new sectors are added and the old ones are removed. We will now add two public functions that will allow the player's cell and sector coordinates to be accessed from a blueprint. The reason we want to do this is so that we can easily display them in the game for debugging purposes using the UI. When we define these two functions, we will use the uFunction macro with the argument blueprint_pure to designate them as functions that the Unreal Editor will recognize. Now, inside of a blueprint, we will be able to find these two functions and call them as pure functions. We will also use the category argument to help organize where the functions show up in the menu when we search for them. We can also use the const keyword after the function's signature to communicate to the compiler that these functions will not make any changes to the class when they are called. This is roughly equivalent to calling them pure with respect to the blueprints. Let's now implement both of these functions. They will simply return the variables we have just calculated in the tick method. Let's now build the project again and check for any errors, because we're essentially done with all of the C++ code. The problem that we are seeing with this error is that we actually removed the constructor from the sector component header, but it still exists in the source file. So it throws an error saying it doesn't recognize this function. To fix this, we can simply remove the constructor from the source file. It is not necessary. The default constructor will work fine. Now we can build the project again. It looks like the build has succeeded, so run the project to start up the Unreal Editor again. The first thing we should be sure to do is set the block material for our voxel world actor. Remember, this is essential for the voxel world to be able to render the blocks. Now we will create a widget blueprint we will use to display our debug information. Create a new folder called UI. Inside of this folder, create a new widget blueprint. Select user widget as the parent class and call it WBP_interface. Then open it up in the editor. In the designer for the widget, we will first add a canvas to the hierarchy, and then add a single vertical box. Inside this box, add 3 text objects. Name them text line 1, text line 2, and text line 3. We will use these as 3 separate lines where we can write debug information to the screen. Choose the vertical box and select Size to Content so that it grows to show the full text we display. We also want to make sure that we turn each of these text boxes into a variable. This will allow us to access them from the blueprint graph. We can now go through and delete all of the example text from each box so they start completely empty. After that, we want to open the player controller blueprint. This is where we are going to manage the UI setup. We will start by adding 3 variables to the player controller. Each of these variables will be an object reference. Create a reference to WBP interface, voxel world, and main character. At the end of the begin play function, we can now create the WBP interface widget. Use a reference to self for the owning player input of this node. After that, we can store the return value in our interface ref variable. Then we will call getActorOfClass to locate the voxel world actor and store it in our reference variable. Finally, we will use the built-in function getPlayerPawn and then cast the output to BP main character to set the main character reference. We also want to jump back real quickly and make sure that we add the interface to the viewport after we create it. This ensures we can actually see the widget on screen while playing. We will now introduce a function that will handle the display of all the debug information we want to show. Call this function displayDebug. It doesn't need any inputs or outputs. To start this function, we will use the Voxel world ref to call getPlayerCellCoordinate. This is the function we defined with the ufunction macro in the C++ file. We can then use this value to set the text variable for text line 1. We will use a format text node to insert the location components into a text string. After you type in the format string and press enter, then you'll see the new inputs for the placeholders show up on the node. We will now use the exact same procedure to display the player's sector coordinate. Finally, we want to use text line 3 to display the current movement kind for the player. We will just use a switch statement and then output a different string for each kind. The last step is to call this function every tick. Let's now play the level and see if there are any bugs we need to fix. Okay, so we can see that blocks are being drawn, but it looks like all sectors are being drawn at the same sector coordinate, which is 0, 0. And it also looks like we are off by 1 when it comes to the block textures, because one of them is all black. And we also need to make a small fix to the player location offset, because it's not calculating exactly where the feet should be. Let's look back at the C++ code and fix up these issues. The first problem we have with the placement of the sectors is related to a problem in the sector coordinate to cell coordinate function. This operation here is supposed to be a multiplication, but I accidentally used the bitwise AND operator. This led to all of the sectors being placed at 0, 0, 0. There's one other error I made in the sector index to sector coordinate function. Both of these divisors in this function should be world size in sectors x. This is because we are doing the index to coordinate conversion, and that requires the quotient and remainder from the same division operation. This is another case where it wouldn't have caused any problems just because our world size is the same in the x and y dimensions. So accidentally swapping them didn't change anything, but we still need to fix it in case this ever changes. Let's now rebuild the project and test to see if this fixes the sector placement problem. Okay, now we do see sectors placed correctly around the world. Let's move on to fixing the black textures for some of the blocks now. This bug is caused by the way we select a block kind in the generate world function. The problem is that we are not starting at 0 for the range. We are starting at 1 to skip the none block. This means we need to reduce the max by 1 so that we don't go past the end of our block kind enum. Now, we can test the project again to see if we have fixed the black textures. Okay, now we only see the 4 block kinds that we expected. The last bug is a little harder to see while playing the level, but I did not calculate the player location offset correctly. Let's look at this calculation a bit more closely because it can be slightly confusing. We want to calculate the light blue line in this image. This is the distance we need to move down from the actor location to get to the position we will consider to be the feet of the player. If we moved down by the capsule half height, then we would get the position at the very bottom of the capsule. We don't want to use this position because it is possible the player will go slightly below the ground due to gravity pulling the player down each frame. We don't want the player's cell coordinate to suddenly jump to the cell below while they are standing still on the ground just because they have technically moved slightly into the ground due to gravity. Instead, we will use a position that is 1 capsule radius above the ground. This will authentically represent the player's feet without leading to any boundary issues. To get this offset, we need to take the capsule half height and subtract the capsule radius. This will give us the exact light blue offset we want from this image. Then, anytime we want to calculate the player's world position, we will take their actor location and subtract this player location offset. We only need to calculate this offset one time at the beginning of the game because the player's capsule size will remain constant. Let's now use this to apply a fix to our code. We first need to get access to the capsule's scaled radius just like we did with the half height. Once we have both of these values, we can calculate the offset by simply subtracting the radius from the half height. To make this easier to test, let's also temporarily change our terrain min and max values. We will set the min to 0 and the max to 1. This will allow us to see if the cell coordinate is being calculated correctly, because we know all of the blocks will either be at z equals 0 or z equals 1. Let's now build and run the project one last time. Drop down to the blocks, and you should always see a cell coordinate of either 1 or 2. This is because we will be standing on top of the blocks, so we should see values that are 1 more than the height of the block we are standing on. Alright, now everything looks good. This completes the first part of this build. In the next video, we will introduce the ability to add or remove blocks from the world.